The situation with the car and the magnet is in many ways analogous to the situation you encountered in your recent homework, where you have a spring and a mass on an incline. Now the spring and the mass and incline, you can be on with a spring at the top of the incline, so it tends to push or pull, and if the spring is compressed, it tends to enhance the force of the gravitational component parallel to the incline. And you can also have this situation where the gravitational component of the weight is in the direction opposite the direction of the force of the compressed spring. Okay, so we draw a few diagrams here to just get a little better handle on force diagrams and what they might have to do with kinetic energy. And we didn't get to go into this in great detail. We were out of time, but here we see at least the beginnings of how we construct these graphs and so forth. Okay, now we assume there's no friction. That's kind of implicit. I didn't actually state it on the board. You have your spring force versus position here. And that's actually the form K times initial or unstretched length, unstretched, uncompressed length of the spring minus your position x. And you can think about why that is. It's not too hard to understand that. In any case, you know that an ideal spring exerts a force that's linearly dependent on its length. So the graph will have to be a straight line. This is force versus position. And intuitively we understand that if you start with a compressed spring, you start with a force down the incline, which is going to be implicitly a positive direction. So you have a force that looks like this. Now, if you go beyond the unstretched, uncompressed, I was looking for one word for both of those things, but unstretched, uncompressed length of the spring, that's where the spring exerts no force. Then it starts exerting a negative force because you go beyond that and you're stretching it and it's pulling back. So you start out compressed with a positive force. Force decreases as the spring uncompresses or decompresses, gets to the uncompressed, unstretched length, but then moves beyond that length and the spring starts pulling backward. So you have a negative force at that point. So this thing just keeps going, at least, well, yeah, that's versus position. And you can get into a harmonic motion situation. We're not going to talk about that yet. It's important to understand, though, when we get to that. Okay. The parallel gravitational component, meaning here's just a quick little drawing of your mg with your tilted axis and your component in the direction of the incline and your component of that force perpendicular to the direction of the incline. This force contributes to the acceleration of the mass. And that's the force we have here. We call that the parallel gravitational component versus position. If it's a straight incline, if the slope doesn't change, then that's constant, because this diagram applies at any point on the incline. So we again have a constant force. Over here, we then add these two. So this dotted line represents this, and this dotted line represents this, and when we add this to this, this raises every point here by this much. So you get a net force diagram here. And again, you have increasing kinetic energy. So you have the area under here, gives you the point at which your kinetic energy starts changing, starts decreasing. And the area under the curve gives you the kinetic energy at that point, which is the maximum kinetic energy of the system. So you might want to think through what I just said. I want to replay that because it's kind of important, and I think I said it right. Up here we just indicate if you got some net force, and this is not the spring, this is any old net force. Again, the work is the integral of the net force times with respect to position, and that's your change in kinetic energy. So that between this position and this position, where x equals a, this is x equals 0 to x equals a, the area under here represents the integral of this integral from here to here, and that's the work done, which is your kinetic energy gain. So again, down here, you see how that applies. You hopefully see how that applies. Another situation that's in some ways more analogous to the one we saw with the magnetic force and frictional force on the rolling car is where the spring is pushing uphill. It's kind of like a magnetic force pushing against a frictional force, because you have the spring pushing up here. Now, of course, it gets long enough, it starts pulling back, and you know that often typically needs to be dealt with. But at least when the spring is compressed, you have a decreasing spring force in this direction and a constant gravitational component. Okay, so the decreasing spring force is like the decreasing magnetic force, and the constant gravitational component of the constant component of the weight of the object back down the incline behaves like a constant frictional force. Now the function for the spring, well, you have a straight line. For the magnet, it's a steep decline, then a very gradual approach to zero. So the graphs look a little bit different, but the ideas are the same, and they apply to the problems that I noticed that some people have a little bit of difficulty with, which is not surprising because the problems are getting a little bit tricky. Okay, so here we have the kinetic energy gain, and then here we have the kinetic energy loss up to whatever this position is. So the question is, first of all, where does this graph end? This implicitly being the net force, this being the spring force, and this dotted line here being the constant gravitational component parallel to the incline. Where's the spring force 0? You know, what happens? Okay, in terms of this graph, are there places where the graph just has to stop, where you leave the domain of the situation? Well, that's getting a little abstract. But this kind of analysis you can apply to a wide variety of problems, and especially to the magnet and cart, which we're going to analyze in quite a bit of detail in conjunction with the lab.